Webinar today, Payment Analytics, the next big step in uncovering errors. My name is Judy Andrian. I'll be facilitating today's event. I just want to note that this webinar is sponsored by the NHCAA, the National Healthcare Anti-Fraud Association. So the topic of our webinar today will focus on cutting-edge techniques employed in payment analytics solutions, and we'll highlight real-world examples. Despite the vast amounts of data available in healthcare today, many industry players use only the most basic data and analytics to identify payment errors. The focus of this webinar will be on more refined statistical methods and the use of new data sources. Our agenda today will include the following. I'll give you a little quick review of our webinar protocols, introduce our two speakers, and then we'll begin with a background and industry problems. The speakers will then dive into various analytic techniques, and we'll try to reserve at least 10 minutes for questions and answers at the end. So before we begin, let me start with a few housekeeping notes and protocols. Please note that your line will be automatically muted during the webinar. If you do have a question or comment, you can send those at any time using the question function located on the side panel. We will address those questions at the end of the webinar, and if we don't get to all of your questions, we'll answer them via email after the webinar. We'll also include in this email a link to a recording of the webinar, so if you think you've missed anything, you can go back and review it later. So finally, if you are attending this webinar to receive NHCAA credits, we'll also in that email provide a link to the NHCAA attestation following the webinar. And to obtain credit, you have to keep in mind that you must complete this attestation by Thursday, October 30th. So I'd like to now introduce today's speakers. Roger Smith is Senior Vice President of Payment Integrity at SCIO Health Analytics. Roger has over 14 years of operational and industry experience in healthcare, claims operation, industry regulation, fraud, waste, and abuse, and payment integrity. After receiving a Juris Doctorate from New York University School of Law, he was in private practice as a commercial litigator for 8 years. Roger led the Special Investigations Unit at Oxford Health, and as well as a group tasked with addressing systemic overpayments, which together increased results by over 300% during his tenure, saving the company over $50 million. Roger has a leadership role in developing SCIO's analytic capabilities in payment integrity. Our second speaker is Leela Kambura Raja. He's the lead SME at SCIO Health Analytics with well over 13 years of work experience, including 8 years of experience in U.S. healthcare domain expertise. Leela is a forerunner in the SCIO's analytical organization. He works with clients to develop strategy for analytical models and is also responsible for successfully delivering successful delivery and implementation. His knowledge of claims life cycle places him under the SCIO innovation team in new product development. He also has experience in healthcare pre-sales as project lead and has worked as domain SME in the sales team. So now I think we're finally ready to begin the webinar. Let me first welcome again Roger Smith. Roger? It's all yours. I think Roger is muted.
I am. Here I am. Sorry about that. Thanks so much. And I am going to try to move the slides. I think we're having a little technical difficulty on that. Judy, if you could also get to work on that, that'd be great. I am not having success in making that happen. All right. So the first thing we wanted to do was talk a little bit about the background in healthcare and why this is an important area. I think we all know that healthcare is a very large portion of our economy, and there's a huge amount of spending in healthcare. In fact, in 2013, over $2.9 trillion of total expenditure occurred in healthcare, which is about 18% of our total GDP. That's actually second only to financial services. There we go, as you can see here. So, and if actually healthcare were its own country, it would be the 5th largest economy in the world. So a significant spend involved. And in fact, it's trending at a pretty high rate. There's been some reductions in that, or some, not reductions in spend, but reduced trend over the last couple of years, but still from 2000 to 2011, you can see the spend in healthcare basically doubled. So a significant problem. And actually, the other piece of this is the amount of data in healthcare is also growing significantly. So as the next slide shows, right now the world has over 900 exabytes of data. And for those that are not data techies, that's actually 1 billion gigabytes. So it's a huge amount of data. And actually, according to IDC, in 2010 alone, over 1 zettabyte of data, which is 1 million petabytes or 1,000 exabytes, so even more, was generated. Not all of it was recorded and saved, but there's a lot of data being generated, and actually by 2014 that number is expected to grow to over 7 zettabytes a year. And a lot of this is fueled by the rise of machine-generated data. So I think there's a lot of new data sources, a lot of data out there. The question is, as data continues to grow, are existing techniques going to work? Are there new things that need to be done? And in healthcare as well, there's really an explosion of data. So as the next slide reflects, in 2012, the estimates are there was about 500 petabytes of data in the world, and that is estimated to grow to 25,000 petabytes by 2012. And 1,000 petabytes is 1 exabyte. So big, big numbers, lots and lots of data that's out there. It's all different kind of sources. It comes from providers, payers, patients. And as that data becomes more electronic, medical records are becoming electronic, et cetera, and more accessible, new ways to handle these very large amounts of data are going to be important. So what's the challenge posed by the size of healthcare and the amount of data? Slide 10 reflects that a lot of folks out there historically, I'm sorry, there's slide 9. So, and data is expected to grow 50 times in the 8 years between 2012 and 2020. So flipping to the next slide, what a lot of people have been doing in healthcare is they've been analyzing for fraud, waste, and abuse for years, and in fact, frankly, decades. There's a lot of experience, a lot of folks that have been doing this for a long time, have really good understanding of some of the common schemes and how some things occur. But despite all those efforts and the continued work that's being done, estimates still are that a substantial portion of payments are incorrect. So the search testing done by Medicare, even in 2013, found that over 10% of the payments for Medicare were improper. That's actually up from 2012, sort of counterintuitive. You would have thought with all the work that's being done, the error rate would be declining, but it's not. And call that noise in the system. The reality is it's somewhere between 8 and 10%. That's a very high number. $36 billion is what Medicare estimated for itself in 2013 alone. And so at some point, as on the next slide, especially with the explosion of the source data and the various types of complexity of services, experience alone is not enough. And so new ways need to be discovered to search through the data and analyze and find patterns and find things that merit review. Just quickly on slide 12, wanted to talk briefly about how some other industries are doing this. Healthcare is not alone in having huge amounts of data. In fact, financial services has, if not more data than healthcare, as much. And they, like healthcare, a lot of it is around services, not actual goods. So there's a lot of value to be added from analyzing that data. Credit cards companies have been doing it for years, and they've been applying actually real-time analytics since credit card transactions occur in real time, and their flags on those occur in real time. Interestingly, the estimates worldwide of credit card fraud are about $5.5 billion, so the problem is much more extensive in healthcare than it appears to be even in credit cards. Other risk management functions within financial services also use data and new analytics extensively. So looking at new ways to pull in data, for example, social media, credit scores, et cetera, that might exist on insureds or specific locations to determine if there are unusual patterns or indicators of risk of loss, as well as new data gathering techniques such as the snapshot device used by Progressive to gather information on driving patterns and history of its insureds and perform rating activity. On slide 13 is some industry information about estimated value of big data and doing analytics in healthcare. The estimates are over $300 billion are available, and that's the size of the opportunity. There are sort of 5 different areas, as you can see. And advanced fraud detection is, in that bottom center section, one of the larger, the third largest, together with some other items it's classified with. So real substantial opportunity to do more is what industry sources agree in the fraud, waste, and abuse detection. Next thing we wanted to do is do a quick poll question for folks. Some folks have probably seen this before. What we have is a question that we wanted to ask folks. If you can indicate your answers quickly, we'll gather the results and talk about those. So the question specifically is, what type of approach does your company predominantly use to identify fraud, waste, and abuse? And we're categorizing it in sort of 2 primary ways. One is mostly rules. So rules would be based on historical experience, something that somebody has thought up and identified as a specific item that is of potential concern. The second is primarily some type of statistical analytic, and those would be advanced modeling techniques, regression, some of the other things we're going to talk about today. The third option would be sort of a balanced approach, using rules and analytics. And then the fourth is you may not know what your company does, and that's totally fine. Just want to see what the distribution is of folks on the call. And for those dialing in, we do have a pretty broad audience, I believe, on the call, and I think probably 400 or 500 folks, so a good sample size to do our poll. And let me just pause and see. Judy, I don't know if you feel like we have enough responses.
We've got about 65% of the people voting, so you might want to just give it a couple seconds longer, and then I'll close it out.
Sure, definitely. And I think the question here is, we're certainly going to recognize that there's a lot of folks that have good experienced staff using rules, those kind of things in their organization. There are some that have moved more in the direction of using statistical analytics as well to enhance those rules, or even to go beyond what a traditional rule can do to identify underlying patterns in new and different ways.
Okay, I'm going to close the poll out now.
All right,
Roger, we had 74% of the people voted, so it's a good number.
Great. Do you want to come back to that at the end, or do you want to do that now?
Sure. No, I'm going to share it right now.
All right, great. So looks like a lot of folks say that there's a balance of rules and statistical analytics that are used, and about even between mostly rules and primarily analytics. And then there's about 10% that don't know, which is certainly fine. Not everybody's role would be to be involved in using analytics. And that makes sense to me. The reality is that there are going to be some situations where rules are very applicable, and it's important to have those, and those are efficient. And then there are other situations where the rules can't do enough, and statistical techniques need to be applied to really find more and be more proactive than reactive, as a rule might allow one to be. So that is, appreciate that, and interesting information for folks. All right, so let's move on specifically to talk about some of the techniques, and I'm going to assume looks like a lot of folks are using them. So we wanted to talk first about regression. There's a couple different regression methods that are in use today: linear, logistic, and robust regression. We're going to talk next about some clustering techniques and the technique of clustering and the additive value that comes from that. A technique of kernel density analysis, some machine learning techniques that are in use, and then one specific interesting new technique, Benford's law, that is also additive and can provide some interesting information. All right, so moving on to basic linear regression. And let me first say what we're doing here is trying to provide a basic overview. There's certainly a lot more detail and specificity to some of these techniques. I'm sure there's some folks on the phone that know that very well, and others that they're at different levels. So we're going to try to strike a happy medium between those two. So what linear regression basically does is take a large data set and try to determine what a pattern is from that data set, applying analytics as opposed to a rule. And what that does is basically, as you can see in the chart below, it says, well, if there's an independent variable, what is a change in that independent variable due to the dependent variable? So it maps, if the number of patients goes up for a specific provider, what is the impact of that on their overall paid amount in its simplest form? And it will predict what you would expect based on the data that's in the universe. And then what you can use linear regression to do is then say, okay, well, so you see the red line, that would be the prediction. And there are points on the graph around that line, some close to the line, some farther away from the line. The ones that are very close to the line, the model predicted correctly or very accurately what was going to happen, and those would be normal events. There's also expected to be some variation because nothing is completely linear, so you'd expect some points to be very close to the line. You can see that as well. Others are further away from the prediction, and so the question there is, what is causing that variation? If a point is significantly far away, that might merit some different action. You might think that that is more worthy of investigation. Let me also then introduce Leela again. Leela is on the phone. He's our subject matter expert. He's a statistician, really expert in use of some of these models and leading our effort to work with some clients and others to apply these models. So Leela, do you want to talk a little bit more about how one might use linear regression?
Yeah, thank you, Roger. And we have used linear regression in one of our projects where we have estimated the recovery amount for some in the payment analytics area. The scenario is where we want to estimate the recovery amount for the identified overpayment claims, where once we have identified the claims as overpayment and once we have sent a letter, the client wants to see the expected or amount which we may recover from those claims. So there we have used the linear regression to estimate the recovery amount. So the advantage, the one more advantage I would like to say here for linear regression is it is very consistent because anyone who calculates the trend from the same data set will get the same value, and we can see the best fit line through the data, and we can say whether the model is best fit for this data or not.
So how accurate the prediction is. So one is predicting information. So in the example Leela gave, it was used to say, if there is this overpayment, what is the probability of collecting that? There are situations where items cannot be collected, and so we need to evaluate whether it's worth the effort to pursue those. That also might be used to say, okay, we've got a claim, we haven't paid it yet. Is this one that if we pay, there's a high likelihood of not being able to collect? That might actually be a factor to decide, for example, should that be reviewed before payment is made? That sounds great. Thank you, Leela. So next we wanted to talk about a couple enhancements to basic linear regression that can do some different things and potentially address some of the concerns. So one of the things that can occur with linear regression is that outliers in the base data, and outliers meaning situations that are different from the norm or the sort of average provider or average situation, can skew the output of a linear regression model. So it can basically move that line up or down and make either mask certain providers from being identified as outliers or otherwise make things look different, skew things. Maybe it makes a provider look like more of an outlier than they truly are. So robust regression is a technique that can adjust for that. And basically, in as much layman terms as I can, sort of tests are done to standardize the outputs to adjust for situations where there are unusual data points or unusual data in there. The impact of that is a higher probability. It basically reduces the false probability, the false positive rate when applied correctly. And Leela, you were going to talk about how we use this in some analytics we did of some chiropractors.
Correct. Yeah, sure. And we had many methods available in robust regression, like least absolute value method and upper M method and MM method and least median square methods. And it depend on the the client requirement, we can decide the model which we are going to use it. To say an example, recently we have applied in one of our model where we had a data like, for example, the data looks like 10, 12, 13, 26, 100, and 500. So if you use any other normal regression model, it will identify only 500 as an outlier. So the advantage with this robust regression model, it will identify 500 and 100 also as an outlier. So by this, unlike the G-score, irrespective of nature of data, it will help, robust regression will help us to find the outlier, and also it will take care of the masking effect. So
great.
That's the biggest advantage from this.
All right, and then the other sort of enhanced technique that can be used in regression is what's called logistic regression. And logistic regression is different in a couple ways. One is it predicts the outcome of what's called a categorical dependent variable. That's basically a yes or no, a 0 or a 1. And it is very good at handling multiple independent variables presented simultaneously. The other big difference with logistic regression is it uses historical data to train the model. And the result of having that historical data and training the model based on that data is a much higher true positive rate and therefore lower false positive rate. There's a couple different applications where we've used this. Leela, why don't you talk about one of them?
Yeah, the logistic regression we have applied in one of our subrogation area, where we had a requirement to identify. We were using the edit some of the rules to identify the subrogation claims. So once we identify the subrogation claims, we are creating the case and pursuing the case. But after some time, we have seen some of the false positive rate is increasing in the subrogation area. So we have decided to implement the predictive modeling, the logistic regression model. Apart from using the edit rules, we have used around 213 different kinds of variables, the independent variables for the logistic regression model. And once we implemented, we tried to prioritize the cases, like I can say to decide whether it's a viable case or non-viable case. And in case of subrogation, we have implemented this logistic regression, and it helped a lot to reduce the false positive rate and prioritize the cases.
And so that is an example, Leela, where we had there was a fair bit of historical experience. It was pretty targeted on a specific thing, subrogation, where we are identifying yes, no, is this claim worth in further investigation for potential subrogatability. You were, I think, mentioning to me earlier that one of the limits of logistic regression, however, relates to how you can sort of lift and shift, translate that model to other models easily. You want to talk a little bit about that?
Yeah, the logistic regression model, when when we built a logistic regression model for one particular specialty, and we may not be able to apply the same logistic regression model in the other specialty. But when it comes to ROB-MM, so robust regression model, we can apply the same kind of shell. The same technique can be applied for irrespective of the specialties. And the logistic regression model may overfit, sometimes may overfit when we derive the weightages from the training data set. When we apply that in the test data set, it may overfit. so it may not give the so good results. But the robust regression, it will not have that problem, and it can work for any kind of data sets.
So basically, looking at the specific problem presented and trying to determine which method is a better method. Logistic regression is a very specific, repeatable thing with specific outputs already known, using those to train a model, whereas robust regression, wanting to apply it in multiple different scenarios and not have to do a lot of training each time. Okay, very good. Next, we wanted to talk a little bit about clustering as a technique. And one of the challenges with regression models is that they often, they identify outliers. So basically, they'll look at a universe of data and identify what those outliers are, as we talked a little bit about, some more accurately than others, depending on the circumstances. There often can be a need to distinguish between those outliers and make some decisions. And some of that might be because there could be outliers that are expected outliers, so they're in some ways not outliers. And an example might be a hand surgeon. If you're looking at the orthopedics specialty, if you don't take those hand surgeons out, they're going to look like outliers, and you might inappropriately happen upon them or begin to look at them. So what clustering does is it really groups items based on the similarity of their characteristics, with the concept being that normal items typically belong to large and dense clusters, whereas some of the outliers are small and sparse, and if you can group those together, what you then are able to do is look at a couple of the items in a cluster, or if you already have looked at a couple items in the cluster, determine whether it's valuable to look at the other items in the cluster. So if you knew that one provider was a hand surgeon in a cluster of 5, it would be beneficial to then be able to determine that the other 4 are probably not worth investigation if if the hand surgeon looks like an outlier only because they do very specialized treatments or very specialized surgeries. Leela, did you want to talk a little bit about specific applications of clustering?
Yeah, in our recent project, we have applied the logistic series. We have applied the robust regression and also clustering. By using the robust regression, we were able to, totally we had around 15,000 providers in our data set. And from the 15,000 providers, we are able to identify around 750 providers as an outlier providers. But since it has very huge number of providers as an outlier, we use the clustering technique to see which are the providers can be investigated. So by using that one, we are able to narrow it down to around 75 providers, no, 78. Yeah, we got around 78 providers from the 750 to concentrate up for the further investigation as preliminary investigation. And there are many methods available in the clustering, like partition clustering and k-means clustering and hierarchical clustering and density clustering. And these clustering methods can be decided based on the business requirement and the nature of data. So it's sort of an iterative or analytic process, Leela, then to decide, okay, which specific clustering methodology is going to be a best fit in the circumstances. Correct. Working with a subject matter expert who's going to be able to talk with the analytical person. Yes.
Great. And let me just note, I know that there's the option of asking questions. Please do that. I think what we're going to do is save those mostly till the end and answer those at that time. And as I said, we're hoping to have, as Judy said, hoping to have about 10 minutes to do that, so that's great. The next technique we wanted to talk briefly about was kernel density estimation. This is a technique that is in some ways similar to clustering. The challenge it tries to address is it can be difficult to determine how many clusters to form or exactly what to form into clusters to get the best results, especially where data points are dispersed. So as Leela, as we talked about with clustering, the central cluster of the normal providers or events is going to be big and pretty dense. Some of the outlier situations, it's going to be harder to determine what to group with what. And so what kernel density estimation does is instead of comparing the outlier situation to the mean or median, to sort of the central cluster. It looks for the nearest, as you can see on the chart here. So if you're comparing the red, the provider circled in red, which are few providers look like extreme outliers, instead of comparing them to the providers all the way on the left, which they're very different from, compare them to the nearest mode, to sort of a near similar group, to see how far they are, what their similarities is, what the dissimilarities are, and that will help provide some refinement into what to group into a cluster and how reliable a cluster is in predicting similarity and how reliable your prediction of whether a provider is a true outlier is. So other methods, what they do is, as I say, compare to the Fisk statistical mean or median. So you're getting a comparison from some faraway point. The advantage here is comparing to a much closer point. Leela, you wanted to talk a little bit more about how kernel density estimation works.
Yeah, this kernel density estimation we have implemented in our recent project using the prog-markless procedure. And actually, in this, the advantage with the kernel density method is we are going to calculate the local density factor and local density estimator. So based on these two, when we are calculating, it will smoothen the data, the data available in the data set, and it will not go by the distance. It will go by the density in the nearest data point, and it is so effective in the multimodal data representation, and it will work very well with the noise when we have the noise in the data.
Right. So if the data isn't sort of evenly distributed, smoothly distributed, and as you say, if there are a couple different modes, meaning sort of peaks, determining how to compare data to each other to identify what really looks like an outlier. Great. The thing you also mentioned, Leela, is this might not be a technique for all situations because it has to calculate the LDF and LDE for every variable. It actually is very processing intensive, so it's something that can be very slow, and therefore it should be used in appropriate circumstances, not in every circumstance.
Yeah, right.
Great. All right. Next, we wanted to talk a little bit about some machine learning techniques. So the techniques we've talked about so far typically are things that require a fair bit of human intervention. They require tailoring to specific data. In a lot of situations, regression and other techniques are based on specific either edits or variables that have been set for the circumstances. So some of the, and I think Leela briefly mentioned, some of the models we're working with might have 100, 150 different independent variables that we've determined. So what machine learning does is allow the algorithms and analytic techniques to basically set it up itself to some extent to try to build its own independent variables to determine how to process a situation. And it reduces the need for human intervention. It doesn't in every case eliminate it. So there are, some of these models are what's called supervised, where there's a human intervention to sort of tweak and adjust the model. Others are much more unsupervised, where they really work on their own. And the reason it's called machine learning, and these techniques have that moniker, is basically they are designed to model against human learning or others that learn, so primarily humans, sort of how the machine is designed to learn much as a human brain would learn, maybe on a much more simpler basis, but designed to provide some of those benefits. The three things we want to talk about briefly are neural networks, random forests, and support vector machines. And Leela, I don't know if you wanted to talk a little bit more about machine learning at a high level before we dive into these specifics?
Yeah, like
no?
if you take, yeah, we are good. We are out of time, Roger, right?
No, we're not out of time. But yes, we do want to save some time. So let's move on and talk specifically about neural networks. So this technique, it most closely is intended to model the human brain, and it uses what's are called artificial neurons. And basically, a neuron is created to perform a task based on certain training examples. So it uses example data that you want the item to learn how to process future data that would look similar. So once trained, the neuron will receive and process those future inputs. The difference is that it can actually look back at the output of some of the other nodes or neurons and use that information to make its decision. So it's not an independent, completely independent. It's interdependent on the others. And this can be a chain of neurons. So once that one neuron is done, it activates the next neuron and knows which specific next neuron that would be the best one to activate. And basically, it's trained by an algorithm that modifies the weights of each specific neuron of the model to learn about the task and perform optimally on the training example. So using the prior data, how best to model for future data to reach a similar result. Leela, do you want to talk a little bit about the advantages of why you might use artificial neural networks?
Yeah, and the difference between the other models and the artificial neural network, the other models will have input layer and the output layer, but with the artificial neural network, you'll have the input layer and middle layer and the output layer. The middle layer, as Roger mentioned earlier, it learned from the other neurons available in the data set. Like the first two neurons, from the first two nodes of the output, that's a third we can give as the input to the third node. That's the main advantage in the artificial neural network, and also it will work very well with the large set of data, and it will play very important role in the classification where the data is non-linearly separable. It is unlike other models.
Great. Okay, and the next technique is what's called random forests. And basically, a random forest is a collection of simple what are called tree predictors. Each produces a response when presented with a specific variable. Those trees are less sophisticated than the neurons in a neural network, but basically this is a model that grows over time in response to data. So as additional data and input variables come in, the model builds a much more detailed tree, and then new data as it comes in goes through that tree very specifically. So some of the advantages are they're pretty flexible at incorporating missing data. When that data is encountered, the model actually adjusts to have an optimal prediction. And then, Leela, you want to talk a little bit more about some of the other advantages?
Yeah, the unique feature from the random forest is it doesn't overfit like any other models, and it naturally mixes the mixes of continuous and categorical variables. And also it can be used in the data imputation where we have the missing data, and the random forest still it can impute the data, and it can create the output. And also it provides the variable importances, like the variable importance, like how much important that variable is. That's the advantage from the random forest, and it will create the decision trees. When we get the final output, we'll get the output decision trees, and we'll get the for each trees we'll get the importance of that tree or the variables.
So if we flip to the next slide, you can probably talk a little bit about how that tree building works and what happens in a random forest. We have a brief flow diagram here.
Yeah, actually, when this is called splitting criterion, like it'll try to create a split from the each variable. When it go by one variable, from it'll consider all the other variables which was previously considered. Like, for example, if you have 5 variables in the data, and when it comes to the first variable, it will review the first variable and it will create a root node. And when it comes to the root tree, and when it comes to the second variable, it will go and check the first variable, what is the similarities between these two. And it will try to fit to the first one if it is going to fit the same, and otherwise it will create one more separate tree to the same thing. And again, it will come to the third variable. When it comes to the third variable, it will go and check the first and second variable with the same for the similarities. It will try to map with that. Basically, it is the binary trees it will try to create. They'll call it as Guinea impute takes values. Yeah, there are some technical terms.
Great. All right. And then one more machine learning technique is what is called a support vector machine. So the next slide shows, I think the chart below is very helpful. Basically, what a support vector machine helps is classifying data points that are difficult to otherwise group using traditional techniques. And the problem is they're close to normal events. So if you look at the lower left, the red items are a group. But it's very difficult to actually, A, tell that, and B, draw the line to distinguish those, because if it's mapped linearly, it's unclear which ones are sort of, especially on the border, in the group or out. So what a support vector machine does is basically, theoretically, convert it into a three-dimensional view of the data. And the output is a decision surface, as you can see on the right, sort of that plane that divides the two data into groups, or the data into multiple groups. And it specifically looks at those borderline cases and decides which goes in group A and which goes in group B. And there are some real advantages here to being able to correctly group that cluster so you know which they fall into, as opposed to misclassifying some of these things, some of the events which can lead to false positives, etc. So, Lila, you want to talk a little bit about
the support vector mission? Yeah, the support vector mission, in addition to performing the linear classification, this can efficiently perform the nonlinear classification also, using the kernel trick. And it is implicitly mapping their inputs into high-dimensional future of spaces, which will help to identify the outlier things, which is mixed with the other good things. And SVMs, these support vector missions will be very useful in the handwritten characters identity recognition. And also, it is very useful in the medical sciences to classify the proteins with up to 90% of the compounds classified correctly.
And you and I were also talking about before that it's often better than regression modeling, because especially when data is highly correlated. So yes, there's problems where there's correlation between data that regression may not handle it as well. This is a way to draw those distinctions to basically determine what is truly an unusual, or in a certain group that might merit some review.
Yeah, when it is high correlation structure or observed in the data, the support vector mission performs very well than any other regression models.
And then the last item we wanted to talk about was a model or a technique called Benford's law. And it's basically a new kind of technique, not, it's more of a law of statistics than it is a specific model that might be built. And it is often referred to as the first digit law. And it gives a new sort of perspective when there's already some items that are identified as potentially of concern, how you might refine the selection to more accurately identify which ones are worthy of analysis. And what it says is that for certain types of numbers, and it's really applicable only to numbers, what is the expected distribution of the first digit of those numbers? So, and that's just a distribution between 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And as long as it conforms to the type of number, the type of calculation that is a highly predictive that the distribution should be a certain way among those numbers. Now, it needs to, in effect, not be a number that's subject to some independent manipulation or adjustment. So if it's a calculated number, so if it's a totals resulting from some kind of aggregation, so ledger balances, data warehouse aggregations. If it's a mathematical combination of numbers, price times quantity. If it's transaction level data, payment sales, etc., it's applicable. If it's, however, assigned numbers like checks or invoices, if it's something influenced by human thought, pricing for certain things because of psychological thresholds, it's not applicable. What we have for the last slide is a example of applying Benford's law. And Leela, you can talk us through, the situation we used it and how it helped.
Yeah, the Benford law actually we have used in our one of our pharmacy model. The pharmacy model we have using the around 85 edit rules we have identified. We are able to and applying some statistical techniques. We are able to identify some pharmacies as outlier pharmacies. But the issue, since we had so many chain pharmacies available in US, we had huge number of claims with that pharmacies. And the investigator was facing a problem to, even once we have identified pharmacies and outlier, as a preliminary investigation, the investigator should review some set of claims to decide whether to pursue the case or not. So that's a requirement we had, and we have applied Benford law on the particular outlier pharmacies to narrow it down to identify the particular claims. Actually, we have applied on the charge amount of the claims. We have applied the Benford law, and we calculated the chi-square, and we have seen. And after applying this first digit law, Benford law, and we had an issue like in the same scenario. If you see the scenario in the presentation, once we identified the first digit starting with 2 and 3 as in a possibly fraudulent claims, and even in the 2 and 3 we had huge number of claims, like we had around 2,500 claims. The reviewer may not be able to review all 2,500 claims to decide the case, to pursue the case or not. So here we applied the 2-digit Benford law on that, the identified digit. So once we have identified the two-digit law, yes, Roger.
No, I was just going to say, just to clarify for the audience, this is a circumstance where an on-site audit was being performed of a pharmacy, and the pharmacy had been identified as one meriting review, not necessarily for fraud, but there were reasons why there appeared to be some claims that were anomalous for other reasons. And the purpose was this helped then zero in further on which claims were the most likely to have actual problems, as opposed to just picking potentially randomly or based on some either rules or regression-based analytics. So it's an additional layer of how you would then use and apply selection to optimize the time spent on-site looking at what would otherwise be a very, very large number of claims.
Correct.
All right. And with that, we have reached the end of the prepared portion. I know there's some questions, and let me pull those up, and we'll try to answer some questions in the remaining time we have. So the first question is, what type of input features do we normally use in linear regression? So what type of variables or input features? Leela, I don't know if you want to talk quickly about that.
Yeah, we'll use the dependent variable and independent variable. The dependent variable is the, we can say, outcome. The independent variable is the variables which will give, I'll say with some example. So the scenario, if you take as a person, can be when we are assessing the risk, okay? The linear regression can be used to analyze the risk. For example, if any health insurance company might want to conduct the linear regression graph, and they want to predict the number of claims per customer against their age, and the per customer for the next year. And in that, the independent variables will be age and the previous year age and the previous year claims and their member attributes like age and the state and their life. There are other variables which we can use like diagnosis categories and procedure categories and other things, which we'll call it as independent variable. And the outcome will be the expected number of claims.
And let me just add to that. Leela actually does this, so he's really more in the weeds. But as I've seen sort of conceptually, the way typically this works is folks who understand the situation from a sort of subject matter expertise perspective would look at it and say, we think these are good independent variables. We think these will be predictive of the outcome. There might be, 300 variables to choose from. Can't use all 300. That's too many. So you might say, well, we think, Leela, your example, age, et cetera, those are ones that we believe will be predictive. So those would be tested. And then there's additional work to say, well, there might be some others that could be predictive. We want to test those. So that's some of the refinement of the model. If we give a certain weight to, and there's different weights that would be assigned to the variable in terms of their importance, and then to see how accurately it predicts the outcome. So some of this is a combination of having folks, and there was another question about give some more details about the type of independent variables used. So in some of the models we're developing in the fraud area or fraud, waste, and abuse area, there might be 100, 120 different things, and some of them could be very specific. It could be show me the percentage of the time a provider has a visit on a Sunday, because that would be expected to be low. So if a provider had a high incidence of visits on a Sunday, that might be a predictor of being an outlier. Another could be percentage of services that are radiology services, or percentage of services that involve 5 manipulations as a chiropractor, extra spinal manipulations. So what happened there is there's specific items that are often identified by subject matter experts or folks who have seen those situations before, and those are very complex, right? There could be 100 of them. How do you integrate those together and get them into a combined output? That's where a lot of the techniques come into play. So there's definitely a need to have a combination of statisticians as well as subject matter experts that can work well together and figure out the best combination of what input variables should be used and then what analytic technique is going to do the best job in identifying truly what are some of the outliers. And there might be multiple analytic techniques. So it might be, some robust regression plus overlay clustering on top of that, those kind of things.
Yeah. To add that point, actually, if you want to predict if you come to logistic regression, if you want to predict the person should be diabetic or non-diabetic, that is, the person will be diabetic or non-diabetic is our dependent variable, and the independent variable will be age, gender, and smoking habit, and lifestyle or the work style, and the state. Those can be independent variables.
So Leela, can you hear me?
Yes, Judy.
I think that Roger we were having some audio issues and people are getting dropped off the call, so I'm sure he'll be calling back in. But there were some other questions, and I can ask while he's coming back on.
I'm sorry, yeah, I was kicked off for some reason, technical difficulties. Yeah. So, Leela, another question is, when we spoke about using regression to predict probability of recovering an overpayment, can it be used to estimate the exact amounts that should be recovered?
Yeah, actually we used to estimate the amount, and we had tested that. Again, we'll test the linear regression. When we see that graph, you can see the expected thing and the actual values. And we used to expect in our practical scenario, yes, we were predicting the amount what we can recover from that particular cases.
So you can do both. I think, yeah, before you know the recoverable amount, if you want to predict the recoverable amount, that's one application. It could certainly be used to do that. That might be to prioritize and say, auditing this claim is predicted to generate an overpayment of $5,000 versus auditing another claim is predicted to generate an overpayment of $200. A decision might be made on that. Now, there might be a differential ranking in terms of how likely the 5,000 versus the 200 is, so that would also potentially play into that. But the other example is you already know the amount that is an overpayment. What is the probability that that's actually going to be collectible? And that obviously plays into what's the historical collection experience with that specific provider, with that type of provider, with that area of the country. So there's a bunch of, again, predictors that might play into that, but those could be used for that kind of analysis. So those are just different points in time where you might have different information in what you're trying to predict.
Correct.
There are some pretty technical questions. I don't want to get too technical because in some cases it's probably beyond this audience, and we can certainly, if there's specific questions after the fact, folks can connect with us directly. Leela, there is a question about talking about the types of data sets that are amenable to neural networks. Could you talk a little bit about that?
Yeah, we can use the, they're asking types of data sets like linear data sets and nonlinear data sets.
It doesn't say, but that might be one example. There might be others like, can you use claims data versus EMR data? So there's probably a bunch of different ways you could think about.
We can use the medical records data, even medical data, or we can use the claims data. Both can be used in artificial neural networks.
And in fact, in some of this is really talking about payments, but in some of the applications we use analytics for on the care management or disease management side, we do bring in a lot of other data sources, even more so than we do in payments. So, EMR data is definitely used, information on biometrics, so lab results, information from surveys that members might take, beginning to take in some data from things like some of the personal health monitors, the Nike Fuel Bands and the Jawbones and those kind of things. So there's a lot of different data types. Are those all suitable for neural networks?
Yeah, yes, and there are some functions which we need to extra to a regular artificial neural network. You need to use some extra functions to when we are handling different kinds of data. But for example, if you want to do some if you are handling the combination of linear and non-linear base of data, then we'll use the non-linear function approximating tool and functions to get the good results.
Okay, great.
There are some extra functions we need to use. And there is one more question, Roger. Is there a value to using the variety of methods concurrently to find the fraud?
Yeah.
So actually we are using, as you previously mentioned, even in predicting the recovery amount, we are using it. First, initially we were using logistic regression and linear regression to first one to prioritize the claim and second one to predict the amount, expected amount. The same way, even in fraud, we are using initially we are using some techniques like robust regression techniques and clustering techniques, and in one of our model we have used four techniques together actually. But it will give different purpose in the same model.
It depends on the application, correct, Leela?
Correct.
And so there's definitely value in certain situations of using more than one technique, because and part of it, I think the example you gave where we initially using robust regression had 750 potential outliers, and then we said, well, that's too many. Is there a way to refine that further is perfect. So we would look at the output from one technique and say, okay, is there the need or opportunity to refine this more? Would that be appropriate? In that instance, it was, and the clustering technique was used, and that brought it down, by one more magnitude. So instead of 750, we got 78, much more manageable number. And there's also and you could talk more about this, but the opportunity to adjust and say how many clusters, for example, because that might, there's some techniques to figure out, should I use 5 clusters, should I use 2 clusters, should I use 8
there
clusters?
are different selection methods also which we can use, variable selection methods, and it depends on the technique what we are using and the application and what is the outcome is expected.
Great. Judy, were there any more questions that we wanted to answer?
I think that's it, Roger, and we're out of time. I do want to mention that,
Right.
Several people have asked, because we've had many audio issues and video issues during this, that unfortunately we're beyond our control. So they've asked if we could send the slide deck, which we'll try to do after the webinar, if that's okay. All right, and any questions that come in after that, feel free to contact us. We'll answer those. And we are also recording this webinar, so that we will send you a link to that, the slides, and don't forget that if you're attending the webinar for credits, we'll also send you the link to the attestation. So that's it. Thank you, everyone.
Thank you very much.
Thank you. Bye-bye.